All right, welcome back. Differential equations. We're going to talk about section 1.3 right now. And before we get too much into it, I'm just going to apologize for this whole section. It's a little weird. There's not a lot of problems in it. There's just a lot of talking. Feel free to fast forward through this and maybe get to the last, 10 minutes, 15 minutes of the thing to get to the part that's going to help you with the homework. But nonetheless, okay, we'll talk a little bit about all the other stuff that goes into it. Okay, so in this case, we talk about modeling. Right? And the idea here, okay, is that these always contain assumptions. Okay, like I didn't get the right answer. Like, well, check your assumptions. Okay, so that's always the first thing to do. In more advanced classes, you'll probably list them. Okay. Most of the problems we're going to have, there's like one or two assumptions that you're going to make those, but it's not uncommon. Your junior and senior problems where you might have, a bulleted list of about half a dozen assumptions that they want you to list. So just be aware that, that's the game we play now. Okay. Let's see here. Side note. Okay, so this is more, again, this is not really pertaining to this class so much, but if you ever have to do like a project, you're running an assignment for a class. I mean, I remember doing a class in Q theory, this kind of Q. It's like how long people have to wait in line at the bank on a Friday afternoon. It's definitely the last century's problem. But this has internet things in it too. How do you route which emails go first, kind of things. But I remember my teacher, we have to write a report on this thing. So you run this big experiment on like how many servers, how much lines you have, all the fun stuff. And we got to the end, and I was like, "How do you want it written up?" He was like, "Well, pencil would be good." I'm like, "Thanks, that's incredibly useful." So I'm sitting there with the writer's block, and one of my friends who was a geology major, she's like, "Do you remember all of those nights, all that time we spent writing lab reports?" I'm like, "Yep, sure do." She's like, well, why don't you start with a lab report? Say your purpose. Why did you do this experiment? Not because it was in the assignment, but what were you supposed to find out? I'm going to investigate the difference between, having different queues, different lines, and one server versus one line and many servers. Okay, so do I want this model where people wait in line and go to a whole bunch, or do I want the typical model where we have a whole bunch of lines and then a whole bunch of servers and keep the servers the same so you check? By the way, this is the better way to go. So in America, we have it wrong. Sorry. This is faster. Okay. Purpose. We're going to investigate this particular thing. This was the next thing in our lab reports. We always remember, I always remember copying the procedure dutifully out of our lab report and sprinkling in fairy tales in the middle of it to see whether or not the TA read it. They never did. But, and I don't blame them. I wouldn't have read it either. Okay. But procedure, like, what software do we use? What assumptions do we make? All of those fun things. How did I set up the experiment? What did we do? What kind of random number generator did we use? That was an important thing. So all of that fun stuff of laying out like how you did your experiment. In chemistry lab, you dutifully copy in what they told you to do in the lab manual. Whether or not you actually did it, you still write that down. Okay, then you have analysis. This is where you have your data. This is where you have all your statistics. You have your graphs, you have your sample calculations. This is what work did you do? Like, we set it all up and then you ran it, you press go, and then what happened and what data did you collect? How did you analyze it? All of that fun stuff, okay? And then we have our results. So you have your conclusion in here, okay? Depending on the class, you might put your error analysis here. Like if it's a calculation, you'll have your error analysis. You might have like sources of error in your results, like, human error or measurement error or something like that. But yeah, if you ever have to write a project up, and your teacher gives you the helpful advice of, types would be good, or English would be a good thing to start with. Fine, here, use your good old fashioned freshman chemistry lab format. Works for lots and lots and lots of different projects that you will have to do. So hopefully that will spare you some of the late night panic I had trying to write that report the day before it was due. I didn't say that. Okay, so on to modeling still, and your book goes into this and has a nice little picture for you. I'll recreate some of that picture, but and I'll add a little bit to it. So mostly this is in your book. But when you're in the process of modeling, okay, you're going to form your hypothesis. This would be your purpose in the previous one, right? This is your hypothesis. I don't think I could spell hypothesis, so this is the question you're asking, okay? Okay, you want to quantify this as much as possible. If you've taken statistics, you know what that means. Like, is eating oats over eating frosted flakes going to be better for your cholesterol? Or eating oatmeal versus eating other breakfast cereals going to be better for your cholesterol? And then you'll match that out. You're also going to put your assumptions in here, okay? Then, let's see, what do we have here? We're going to write our mathematical equations here. So if you have an equation to write, this is a good place to do it, okay? We're going to then solve said equation, okay? And you're going to get your solution, okay? I do have a good story for you on this one. So then we are going to check the model. Check your model results with actual data, with reality. Okay, a lot of people like to predict the stock market. The way you do that is you take half of your data, you write your mathematical equation with what you think is going to happen, solve it, get your solution, and then test it with the other half of your data and find out that nothing works. Okay, by the way, if somebody ever tries to sell you, like, this is a surefire way of picking a stock, that person is about to rip somebody off. I hope it's not you. Okay, but in your model here, okay, one thing you should always do here is check with an expert. Okay, one of the things that I had to do when I worked for the aerospace company was a lot of the people who actually put satellites up are retired, and they were retiring during the era that I was working there. And the old engineers, they always worked in ratios. They didn't, they liked ratios. They liked them so much that they didn't just use ratios, they used ratios of ratios. At which point the computer scientist said, "You're the math guy, you figure it out." I was like, really? So yeah, let's go. So I wrote, some equations down, based off of what their rules of thumb and what their ratios were, because they didn't, they did have computers, but most of it was done with slide rules back in the day. So we came up with some, I came up with some equations. They refined them so they couldn't quite use the, looks like 2.5 there. Like, no, we're not doing that. We're coming up with an actual number here for us. But one of the equations I came up with had like fourth roots in it. Okay, it had like an a to the 3/4 or something. And this was like a change. So technically, I guess it's a dA. This was a change in like a weight. And I asked him, I was like, "Hey, if your weight goes down, you're going to get imaginary numbers, and that doesn't really work." And then they laughed at me because they had to explain to me that if the total weight on a satellite goes down, you find something else to stuff into that satellite so that the weight doesn't go down. So if there's an extra camera you can put on there, you put that in there. The weight never goes down. So if they had to explain to me, like, no, man, this is a government project here. We don't spend less money. We spend more. There's no minuses here. So check, and I'm glad I did. Check with experts before you present this to your boss, because this would have been a disaster. But so I had to do some reworking on that, but it wasn't too bad. Okay. Pretty much it was just like, oh, here's my assumption. Okay. DA always has to be positive. So that didn't make sense to me, because I've never put a satellite in orbit. So yeah, check with experts, make sure that your model makes sense with them. Like I said, test it out a couple of times, test out a couple of scenarios so you can ask good questions. But that's their process of modeling, of going around the circle. And of course here you're going to refine it. Okay, so you can either change your assumptions, refine your question, and then go around the circle all over again. And I've got another story for you about that one too. So I have an uncle who pretty much got an eighth grade education and said, that's enough. I'm going to go work now. And he built a house. And for some bizarre reason, he wanted to build a house that had an octagonal roof. And he asked me to figure out how many shingles, how many roofing tiles he would need. So I needed to figure out the area of an octagon. I didn't know the area of an octagon. So, I did the standard thing, right? I made a whole bunch of little isosceles triangles, and then, figured out how to do that, and came up with an answer and gave it to him. But before I gave him that answer, because I know this guy, and if I give him a wrong answer, he's going to mock me until the end of his days, or the end of mine, whichever comes first. So what I did was I drew a circle around the shape. I knew what the radius is. He didn't know the radius. He knew the length. We didn't know the radius. Knew the diameter. Like this side, this whole thing, that was fine. But half of it, no, we didn't have that. But that's okay. But I took the octagon, and I inscribed a circle around it, and figured out what that area was, to make sure that the area I found for the octagon actually worked out. So a lot of the things that we're going to show you, that's great, but that's like your first approximation for what's going to happen for you. All right, back to stuff that actually matters for you right now. Okay, so first model we have that's very common, you've actually studied these before in college algebra and pre-calculus, are population models. Okay, these are, nobody will ever ask you this, nor will I. Okay, these are called Malthusian models, named after, cleverly, a guy named Malthusian, or Malthusia, and this is about 18th century stuff, so late 1700s, early 1800s. Okay, and the whole idea here is that what they were going to say is that the rate of your population is going to be proportional to the number of populations you have. You got a few rabbits, they're going to make a few rabbits in return. You got a lot of rabbits, they're going to make a lot of rabbits. Okay, people work the same way. Okay, but that's the kind of thing, and I'm sure that you've never seen this symbol because they stopped using it. It means proportional to, and the immediate thing to do, and this is what happened when I went to school, the immediate thing you do is you use a symbol that you know, right? And you say K is your constant of proportionality. Okay, so the first thing you do is like, oh, it's proportional to that. I'm like, okay, it's equal to a constant of proportionality times the quantity you're looking for. Okay. So this is a population model. If you remember back to college algebra, we're going to solve this eventually, and you're going to get a P of t is equal to this thing, e to the constant of proportionality, kt. Okay. So we'll get there, but not today. This whole section is simply talking about how to set this stuff up. We're not solving a thing in this section. We're just setting it all up. Okay, so that's why I apologize for the fact that there's a lot of talking, not a lot of doing in this particular section. Okay, so yeah, that's that's what we have for this. This also works for radioactive decay. you got a lot of radioactive material, there's going to be a lot of radiation put out. So I think the algebra book uses a Q, okay, and that's proportional to the amount of stuff that you have. Or, right, you could say that the change in the amount of stuff that's radioactive is proportional to the amount of stuff that you have. So the rate of change is proportional to the amount you started with. Okay. Again, that kind of makes sense, right? I mean, we live on this planet, we deal with radioactive materials. If you have a minor exposure, that's not too much to be worried about, but if there's a lot of radioactive material somewhere and it puts out a lot of radiation, okay, then there's something more to be worried about. Okay. And they also talk about continuous interest, right? Where, and again, I think your book uses a DA. Okay, we used P. No, we used A. We used A. We just said the initial amount. A0 was P. So, capitalist society, the amount of money you're going to make on interest is proportional to the amount of money you got in the bank. I know that's revolutionary, but what we're going to say is dA by dt is equal to, or is proportional, or is equal to the constant of proportionality. That'd be your interest rate times your amount. Okay, and I think this ended up being this equation. Principal is a sub 0, so a sub 0 here be P for principal. To the R T, it's really important. R is expressed as decimal. So if they say your constant proportionality is 3%, right, it's up to you to say 0.03. If you just use a 3, that's 300%. And if you're looking at that and thinking, those numbers look right, I'm going to recommend that maybe you find a career in loan sharking or title loans for, or payday loans or something like that, because that's what they do. Okay. So that's one set of models that we come up with. They're effectively, right, all the same, but it's nice that they apply to all of these different things. The chemical models, I'll probably throw you 1 or 2 problems like this in the homework. Mostly you're going to be able to get these by pretty much following an example. They don't expect you to be able to do the chemistry to understand what's going on a lot, okay? So they're going to tell you, like, this reaction depends on these 2 things, okay? So let's see here. Let me show you the second one I have here. So what do they have? They have, and I have no idea what these chemicals are. I mean, this is, carbon, hydrogen, 3 hydrogens, chloride. Okay, makes sense. Carbon has 4 little bonds to deal with, and we filled them up. And we're gonna, this is NaOH, so sodium hydroxide there, I guess. And we're going to CH3OH. It's an alcohol. OHs are alcohols? I think they are. Plus salt. I know what NaCl is. Okay. And this is still given. Okay, so don't worry. Like, it's been a couple of years since I've had chemistry class. They give you that this reaction. This is dependent on amount of CH3OH and NaCl, okay, or NaOH, sorry. So this is dependent on the amount of stuff that is present, okay, and it's dependent on both of these things. So let's see if we can come up with their actual question. I think they had, where do I put my question here? Okay, this is, so the reaction, that's a rate, by the way. The reaction is a D amount by time. So if we say let X be amount CH3OH, that's the stuff I'm looking for. Then the amount that's happening, dx/dt, right? Where did I write that down for you? This is the rate of CH3OH. That by time, so that's the amount that's increasing here. We're going to say we have the reaction. Oops, sorry about that. So it's done is greater than 0. Okay, again, assumption. What we're going to say is that this depends on, or this is proportional to, that's what they say, is proportional to the product of the amount remaining of CH3Cl and NaOH. Okay, so it's the product of the amounts remaining of these two chemicals. So we're going to set A is equal to amount of CH3Cl, and then B, they use Greek letters, they use alpha and beta in the book, of NaOH. Okay, so we're going to say that dx/dt, right, is proportional to, equals the constant of proportionality of A minus X, that's the amount that remains, B minus X. All right, and I promise you that I know these are confusing, so I promise you that when I throw you a question like this, I will make it very similar to the example that's in the book, so that it's not on you to be expert in chemistry to be able to solve this problem. Okay, so just don't. I know when you're going to go read this, it's going to be a little bit off. Okay, so I'm going to go ahead and pause this for a moment and get my food done, and then keep going. All right, halfway through, promise. Okay, and sorry about that. Okay, the next common, so this is a kind, oh, by the way, they call this a, what is this? This is a second order reaction in chemistry. There's 1, 2 things that we're dealing with. So if you're setting this up and you have something called a 13th order reaction, if you don't have like little 13 terms over here, you got to go back and check. Okay, so understand that that's what's going on here. I'm not going to give you too many of these. All right. Conversely, mixtures. Okay, I know some of you were taunted and harassed in Calc 2 for this. I don't make my students go all the way through this for Calc 2 because we talk about it here. Okay, and the canonical problem is mixing 2 salt solutions. These get kind of crazy. Okay, I don't ask you like the really crazy ones, but I've seen setups where they have like one salt solution is being poured into another, which is being poured into another, which is being poured into another, which is being poured into another, and then it's finally free. And you have to figure out like what's the salt in each tank at any particular time. Yeah, we're not going through all of that. Okay, we're going to keep this pretty tame. It'll get hard enough just with a simple sort of thing here. So we're going to mix 2 salt solutions of different concentrations. Okay, so a very typical problem will be like maybe and salt just means like we added something to the water. Okay, it doesn't have to mean NaCl. It could mean anything you put into the water that dissolves. It could be mixed. Okay, so you might be taking, like a class of groundwater or something, and you've got, let's just go with the example I came up with. Okay, so we'll have a tank that say this is 100 liters. Okay, that's about 25 gallons. Okay, so moderately expensive fish tank, so somewhere about $150 for a fish tank, 25-gallon fish tank, and it's got a certain amount of salt in it, and by salt I mean food coloring. Okay, and then we're going to pour in something that says has maybe more food coloring in it. Okay, and then we're going to drain this out at the same rate that it's coming in. Okay, as soon as we start changing, like maybe it could drain faster and maybe it could drain slower, things get kind of tough. But this is the beginning part, so we're going to keep this the same as that. So inflow and outflow are the same for this case. Okay, the assumption that they always make here is it's well mixed. Okay, that there's like a little propeller or contraption down here spinning all the water around so everything gets mixed up before it gets drained off. Okay, and your job is to tell me, well, how much food coloring is in the tank at any one time. Okay, and again, we say salt, but they could be a pollutant. It could be, in any case, if you're doing this for, an engineering lab, this might be food coloring, but whatever you're adding to the water and mixing up and it's draining off. Okay, and the way we approach these problems, okay, is that the change in salt, okay, everything is salt, okay, is equal to the rate of salt in minus the rate of salt out. Okay, revolutionary, I know. So rate of salt in minus rate of salt out, that is equal to the change of salt. Okay, so let's come up with a better equation for this. All right, so we'll say here's my amount of salt in over amount of salt out, and then we'll say this is equal to, and then we'll have like the rate in. So this might be something. What did I put for this? This was 2 liters per minute. Okay, so this is also going to be 2 liters per minute. We have initial concentration. Okay, these are all going to be given to you like in paragraph form, so you're going to have to start, but they'll say something like the original, the tank was set up to have, what did I say for this one? I try to use a different example than your vocab, so I had to make up my own numbers. Okay, did I not do that? That we have 300 grams per liter of salt in the tank. Okay, so 300 grams per liter in the tank when it starts. Okay, and this stuff coming in has a concentration of, let's say, this is at 70 grams of salt per liter. Okay, and then we have to figure out how much is coming out. We don't know. Okay, so rate in, that's like the 2 liters per minute, 2 liters per minute times the concentration in. Okay, minus the rate out. Again, that's going to be the 2. Okay, times the concentration out. All right. So flow in times concentration in, flow out, concentration out. Okay. Well, they tell us what the concentration is coming in, right? We could figure this out. So we could say the rate in times the concentration in. Right, this is the amount of salt coming in. So we have 2 liters per minute coming in times, what did we say? We said this is 70 grams salt per liter. Notice that the liters cancel and we are left with, we are coming in with 140 grams of salt per minute. Okay, that seems like a reasonable rate in, right? This is the rate of salt that's coming in. Okay, now the rate out, okay, that's not so bad. Rate out is not so bad. But the concentration out, that's where it's going to get a little interesting, because one of the variables we're going to define is, this is Q, this is the amount of salt in the tank. Okay, so the rate out, that's our 2 liters per minute, right? And coming in is going out. Tank's not going to empty, tank's not going to overflow. Okay, but the concentration out, like, I don't know, how much salt is in there? Because we need to know, like, how much grams per liter is in here. And we just don't know. So there's a certain amount of salt in the tank divided by, what did we say this was? This was 100 liters divided by 100 liters. Okay, so this is 2 liters per minute times Q grams per liter. So we have Q grams per minute is going out. So we still have the same units. If you like to check the units, it's always a good thing to do. Okay, but we have 140 grams of salt coming in per minute, and we have Q grams of salt per minute leaving. Okay, and it is our job to figure out what's going on here. So we take our limit, and we get dq by dt, d, is equal to a constant that's coming in. So it's 140, right, minus how much is leaving. And that is going to be 2 over 100, so that's 2q over 100. That strikes me as something we could do, right? That's dq dt is equal to 140 minus q over 50. And then we'll swing this to the other side because this is how you're going to solve it later on. Plus q over 50 is equal to 140. Okay, you actually have a choice of how you want to solve this thing. But that is, you know, that's the equation that they're looking for. They just want you to set this thing up. Okay, and I'm sure we could do all sorts of wacky things where it doesn't have to be 70 grams of salt per minute. We could have some kind of a weird little seesaw type thing where it's tipping back and forth, allowing more salt to go in if it's this way, but as it goes up, there's less and less salt that's flowing into this setup, this system. So this might be a function. All sorts of things can go wrong, okay, and they will. But for now, we're just asking you, could you set something like this up? We're not solving it. We're just saying, can you set this up? Okay. We're not going to worry about trying to solve it until the next chapter. Okay. Say. Now, the next one is the last one. Okay. Is it? It is. It's the last one. Okay. So, suppose we have a zombie outbreak. On a cruise ship. It's an isolated system. There's not extra people going in and going out. Otherwise, this model gets to be a little bit more complicated. Okay, that's why. And you know, if you watched any zombie movies at all, you know it's contagious, right? The zombie breaks down, eats you, and then you turn into a zombie. So it is definitely contagious. I mean, you could use this for any contagious disease, like, you know, COVID. But this actually is the original models that people used to do this. Okay. And the ship, okay, the ship has 5,000 people on it. Okay, passengers and crew, 5,000. Yeah, that's our total population. The rate at which the disease spreads. Is proportional to the product of how many people are sick, or in this case, how many zombies we have, and the remaining passengers, the remaining people. Okay, so we have zombies versus people. Okay, so let's see. Right, I think that's all we really need. Again, in an actual problem that we're going to get later, and I've given a problem very much like this for on quizzes, this one too. just to let you know, like those are my two favorite word problems: is the disease outbreak and the mixing problem. We're watching a lot of, if you like zombie movies, Train to Busan is the movie that I'm currently watching, like a lot. All right, we'll just turn that on and leave it there. We do. Okay, so we're going to say let Z, of course, Z for zombie, right, equal the number of zombies. Okay, so what we're going to say is that the change in zombies, right, is proportional to, there's our constant of proportionality, to the number of zombies times the number of people that are left. Well, Z plus P would be 5,000, right? Zombies plus people is going to be 5,000 in total. So P would be 5,000 minus Z. So we want 5,000 minus Z. Okay. And that is going to be, right, our model that we're going to do this. We're not solving this. I didn't tell you how many zombies started. Okay. We're just going with, I didn't tell you what the rate of, I didn't say like in hour one, right? Hour one, there was 20 zombies, and 3 hours later, there was 300 zombies. We didn't say that. I would have to say that for you to solve it. Clearly, what we're going to do, we're going to put this as denominator. We're going to use some partial fractions. You're going to love that. And we're going to solve this thing. Okay? So we'll stop with that because this is all they want you to do. Okay? That's it. That's as far as you have to go. So that's our, yeah. I'm not going to do the next one. So that's our 1.3. I'm sorry it took so long, and I'm sorry there's a lot of talk. There's not a lot of action here. So I'm just going to stop there and let you get to your homework, and I'll see you for 2.1.